Okay, good afternoon. Let's start. So last Thursday, we reviewed the different implementation methods for digital circuits. So we have 4 custom SOC approach, structured ASIC FPGA, special domain processors, and general purpose processors. But to obtain the best performance, it is desirable to implement a digital circuit in a fully custom way. However, the cost can be very high and even not feasible for some small company. And the turnaround time can be very long. And the FPGA is the method to meet these 2 challenges. It can lower the cost and reduce the design time. So FPGA can make IC technology more accessible to designers who do not have the knowledge of fabrication processes and design rules. And for those designers who lack the sophisticated IC design skills. And that's the approach. FPGA is the approach for our course, for you. Here shows an FPGA. It's an IC. It's sells as standard parts, but users or you, can program or reprogram the device to perform a hardwired digital function. And since FPGA is a finished product, so the design and manufacturing costs are shared by all the users. So the design cost is low. So the turnaround time is in minutes. You can reprogram it just in minutes, as you will try in next week's tutorial. FPGA is widely used for hardware prototyping and accelerating key functions. It is sometimes used before making an ASIC. An ASIC like this is a semi-customized IC with logic functions determined by the designers. The physical design of these logic functions are pre-designed by the vendors. And they are integrated into an IC with some design automation tools. And this way, we don't save manufacturing costs, but we save the design cost and time. If we compare these 2 approaches, FPGA versus ASIC, regarding the cost. So for the ASIC approach, we have a huge design cost, referred to as non-recurrent engineering cost. And this part, NRE cost, which is there even if you don't make any chip. You need to design and make a mask. So that's the NRE cost here. The NRE cost is high, but the manufacturing cost per chip is low. So if you increase the volume, increase the units, the cost increase slightly, the total cost increase slightly. FPGA has nearly zero non-recurrent engineering costs. We don't need to make mask for the product, for the fabrication. We don't need masks, and design time can be short. So nearly zero NRE costs. But the cost per chip is high. You need to buy it from the FPGA vendor. It may sell, say, each FPGA depends on the model and depends on the level of sophistication. Each FPGA chip can cost greater than $10 to thousands of US dollar. So per unit is high. And for the ASIC, so the cost per die, per chip is low. Of course, depends on the size and technology node. It can be usually is for advanced designs in tens of US dollar. So here, the FPGA cost increased significantly with the number of chips you require. And there is a crossover point here. Below this volume, FPGA has greater advantage in terms of cost. Beyond this volume, ASIC provides lower cost solution. And often this crossover volume is in the 100,000 chips range. So you see, if you have near digital circuit, say in just a few thousands, then FPGA is obviously the best approach. But if you have a large volume, say components used in some consumer products like your smartphone, they are in millions, then ASIC is the better approach. And moreover, this is a cost comparison. If we compare the performance, in general, the ASIC is better in terms of speed, performance, and power consumption, because it's customized. So you can offer 10 times higher speed than FPGA, 10 times lower power consumption than the FPGA for the same application. Now, this chart shows the trend of the design cost for new generations of ASICs. It's for ASICs. It's cost for 65 nanometer. The design cost here can be around $30 million US, $30 million US for a typical design. Increases to 37 million for 40 nanometer. Typically in 28 nanometer, 50 million. Increase significantly this design time, and it's in most advanced technology. The design cost can be, say, more than 500 million US dollar. This design time, design effort, design cost is huge. So only fewer companies can afford this. If we look into the components of the design cost, it includes the fee for software. This is the greatest portion. A modern digital IC contains tens or hundreds of billions of transistors. It must rely on some design automation tools to manage such a huge number. And so it relies on advanced design software. This part is for physical design. That means layout, verification. You need to check whether the design is right. Architecture, therefore design cost. IP verification, IP qualification, that is the cost to verify and the quality provided by a third party IP vendor. IP is intellectual property. It may be a block, like a USB interface block. You may buy it from the market and not designed by yourself. But to verify it still costs designers time and effort. Prototyping, validation, so on. So basically, here this chart says that the design cost increases exponentially for new ASICs. Let's come back to the cost structure of ASIC and FPGA. Say the dash curve here, this is the ASIC cost for generation N, for certain generation. So let's just call it generation N, and this is FPGA cost for the same generation of technology. FPGA has nearly zero NRE cost, and ASIC has a very high NRE cost. So the crossover volumes here. Now for next generation, the ASIC curve is here, cost curve. The design cost or NRE cost increased a lot, but the slope here is smaller, which means the cost per chip reduces. Say for the same function, it may have cost smaller area. So the cost per unit is smaller. Now for FPGA, for the newer generation N+1, the cost per unit also reduces. So the crossover volume for the generation N+1 is greater than the crossover volume for the earlier generation. So that's the impact of technology in this FPGA versus ASIC comparison. So in newer generation, you may prefer FPGA solution, even if you have a large quantity to use. Okay, so any questions regarding this comparison? No, let's move on. So the course is mainly about FPGA. So we spend some, we focus on FPGA. So we look into some details of the FPGA implementation methods. Next week's tutorial, you will go through an FPGA implementation. So what is an FPGA? So earlier last week, I introduced the idea of simple programmable logic devices. So the user can program that simple PLD into a say AND gate, NOR gate, or some form or some any form of sum of product implementation. We can program it. But now we can add another layer of user programmability. That is, you can program how those logic gates are connected together. Apart from setting the logic functions, you can program how the logics are connected. And that's FPGA. So in that way, we have a general programmable logic chip. But it is different from microprocessor, where the program is just the instruction to the fixed hardware. In FPGA, you can program the hardware itself. The wiring of hardware can be programmed. So the first FPGA was introduced by Xilinx to the market in 1985. Xilinx is now a part of AMD. You know which company AMD is, right? It's Advanced Micro Devices. It's another CPU maker, major CPU maker apart from Intel. So FPGA has a structure, a generic structure containing these blocks of uncommitted logics. Logic are waiting to be configured by the user. So the uncommitted logic blocks can be simple gates. Hence, part of the name is gate array. A full name is a few programmable gate array. So the gate arrays in these blocks. And we also have lots of programmable wirings here. So these channels, these spaces here are wirings which can also be programmed. So logic blocks and the interconnect resources. It also provides lots of I/O cells. And these I/O cells can be very flexible. Say there are different logic level standards. Say for TTL, the supply the high is 3.3 volt. Or CMOS can be different. So there are different definition of low and high voltage levels. And for FPGA in general, these I/Os can be programmed or can be set, can be configured by the users for different standards. And nowadays, there are two major players in the FPGA market. Xilinx, now AMD, and Arteria, which was acquired by Intel. It is now a part of Intel. In this course, we'll use a FPGA board provided by Arteria. And there are other specialist FPGA makers for some special domains. They include Actel, Lattice, and Quick Logic. So you see, in FPGA, we have two layers of programmable things. One is the logic, the second is the interconnection. Well, this architecture is one type of FPGA architecture. Someone call it island type, island style. We have symmetrical array, like a matrix of logic elements, and the routing or interconnect are in between those islands, like building blocks and the roads. And this is the dominant type of FPGA architecture. Other types include row-based. So logic blocks are put in a row and with no routing in between. Routing are provided between rows, not between columns. A third style is CF gates, where the logic are below the interconnect, or the interconnect wires are overlaid above the logic blocks. There is no clear distinction between logic blocks and the routing areas. They just overlay with each other. Oh, this is a complex programmable logic device approach, CPLD, hierarchical PLDs. So we have some PLD blocks that interconnect for different PLD blocks. So the core of the FPGA is the so-called is the configurable logic blocks. CLBs, and the silence called CLB. It's the basic FPGA functional units, and the arterial called its logic elements. This so each element is similar to the simple PLD. It can implement a function, any function of say 4 input or 4 input logic. But this logic function is implemented using a lookup table, which I will explain in more details later. Most common with 4 inputs, but modern FPGAs are more complex. They can accept, say, 8 inputs. So there is a lookup table, LUT. And typically an optional flip-flop is provided. A D-type flip-flop is optional, and it can be bypassed by using this multiplexer. Say this multiplexer selects either of its input and pass it to the output. A 4-input LUT can implement any 4-input Boolean equation or a 4-input choose table. Now let's see how the lookup table implements the wanted logic function. Let's look at an example, a real example. Say we wanted to build a half adder, 1-bit adder, half adder without carrier in. So we have A and B inputs. So this is the choose table for the output and some output. So if both inputs are 0, then output is 0. If one of them is 1, some output will be 1. If both inputs are 1, some output will be 0. And that's the addition, binary addition. But there is also a carrier output. The carrier output will be high, will be 1, when both A and B inputs are 1. In other case, the carrier output are 0. So that's the 2 choose tables, and we can say use using discrete components. We can use an exclusive OR gate to implement the sum output, and then AND gate to implement the carrier output. But that's a fixed hardware. In FPGA, we use a lookup table to implement such functions. Here is the way. So we have a small memory. Say we have a 1x4 or 4 rows of memories. Each location is 1 bit. So this is a truth table. So we can store. So we have memory, small memory. Say we have 4 locations there. First location stores 0. Second is 1. Third one is 1. Last one is 0. So this is some output. Then the input is like an address pointing to a specific location of this memory. So if input is 0, 0, then it will point to the first location and pass this value to the output. If input is 1, 1, then it's pointed to this location. And this content stored in the memory will be passed to the output. So we have a small memory, and we use the input as the address of the memory. So yeah, the input is 0, 0, and then it points to this location. Input is 0, 1 points to this location. 1, 0 points to this location. 1, 1 points to this location. It's like 2-bit address. So you can address 4 locations. I point to a location. We'll just store some values using memory, use SRAMs or using D-type flip-flop to store those known values or desired values there. And for the SRAM, for the carrier output, we store another set of data in the memory, in another small memory small memory block. So 0, 0, 0, 1 is stored in that memory. So this is a carrier output. So that's the idea of a lookup table to implement a combinational logic function. So logic input connect to the address input of the memory. Logic output is memory output. So here, say if we have 2 outputs, we can use 2 lookup tables, and each use its own address decoder. So of course, we need an address decoder for the address input. Alternatively, we can combine the address decoder into 1. We can for this particular example, the 1-bit adder, the sum and carrier output, they have the they have the same. They can use the same address decoder, so we can combine them into 1. So if so we have 1 address decoder. So if say we have this 0, 1 input, 0, 1 input is 0, 1, then it points to this row, and we can designate this first column as the sum output, second column as the carrier output. The idea is the same as before, but here we just remove 1 address decoder. I just use 1. So this address, this address pointing to specific location, this needs a decoder. It's kind of hardware. So by combining them together, we can reduce the hardware. So any questions with this lookup table concept? Well, it's simple but very important. It's the fundamental of FPGA. It uses lookup table to implement an arbitrary logic function. Idea is simple, but FPGA just rely on this idea. And well, as I said, it use memories to store those outputs, desired outputs. And this memory could be written again, could be rewritten, so we can reprogram the FPGA easily. And this is a slightly bigger example, a 4 adder, for 1-bit 4 adder. It has a carrier input. So this is a truth table, the desired truth table. So we have input A, B, each of them are binary, and also a carrier input, also binary. We have a sum output and carrier output. So if input for this 0, 0, 0, the sum is 0, carrier output is 0. So if input is like 0, 1, carrier input is 0, then sum is 1, carrier output is 0. Or check this row, A, B are 1, carrier input is 0. So the output should be 0. The carrier output is 1, and so on. So that's a 3-input truth table, and we have 2 outputs. So to implement this 4 adder using a lookup table, so we can use a 3-input lookup table, which means there are 2 to the power 3, 8 rows, equal to 8 rows here, and 2 columns, because we have 2 outputs. One is sum output, the other is carrier output. So we just copy, just try to write this desired outputs into this memory block, and then use the A, B, and carrier in as the address to this memory blocks. 3-bit address, so they are 2 to the power 3, 8 locations. We use an address decoder and to point to certain rows, then pass this stored memory out to the output. So the combination logic can be implemented in a lookup table with the same number of inputs and outputs. Now, the idea, now this is also important, right? The fundamental of programming of FPGA. So we have 2 levels of programming. One is for the logic function, the other is interconnection. And now it's about the logic function. So here is the idea of configuring an FPGA. So the programming and FPGA is not the same as programming and microprocessor. And in programming and microprocessor, you have some instructions to the microprocessor, which has a fixed hardware. But in programming and FPGA, we download a bit stream, not program, some data, bit stream, to an FPGA. And this bit stream will go into this memory locations. They are D-type flip-flop or SRAM cells. Depends on the implementation method. We have some registers there, or D-type flip-flop. We can treat it as registers there. So we download a bit stream to those memory locations. The programming and FPGA is known as configuration. Next week, in your tutorial, you'll see that it takes us only about 1 minute to download a bitstream into FPGA. You write something into FPGA. Basically, you download some bitstream into the memory, into these registers in the FPGA. And all the lookup table are configured using the bitstream. So they can contain the correct values to implement the desired Boolean logic. Now for this chart, let me explain. This is an 4-input lookup table circuit. We can, so the 4-input, or we can treat it as a collection of 2 3-input lookup tables. But anyway, so it's 4 inputs. It has four inputs. In a lookup table, we have A, B, C, D, 4 inputs. And one way to decode this, well, okay, this is like an address input to the memory. And for this memory, because it's 4-bit, we have 2 to the power 4 equal to 16, 16 locations. So we have 16 locations here. 16 locations. Each location contains 1 bit of memory. Can be 1 or 0. So we have stored some 1 and 0s in this registers, memories. Here, Y is the output. Now to decode it, we can use multiplexers. So in this decoder, we have 4 levels of multiplexers. Here, first level, second level, third level, and last level. And multiplexers has multiple inputs and 1 output, and it choose 1 of the input to the output, depending on the control bit. So say, let's look at the last multiplexer. If the D is 0, then the upper input will be passed to the output Y. If the control D is 1, then the lower input will be passed to the output Y. I select 1 of the input to the output. This is a 2-input multiplexer. Now say so here we have another level of multiplexer. So in each input of the last multiplexer, we have another multiplexer. And then in each input of this multiplexer, we have another multiplexer in each input. The decoding is like this. Say input is, so let's say input is, say 1 0 1 0. The decoding process is like this. So D is 0, so the upper pass will be select. C is 1, then this pass will, the lower pass is select. B is 0, so the upper pass is selected. A is 1, and this pass is select. So the memory stored in this register is passed to the output. And each pass is uniquely defined by the address. So this is 4-input lookup table. So then there are 16 values stored in the registers. Configuration of the FPGA means that we set the values of these registers, to either 0 or 1. That's the configuration of an FPGA. It's the fundamental concept of FPGA's programming or configuration. Simple, but this is important for you to understand and working of an FPGA. Well, the combinational logic is important, but in digital circuit, we also need sequential circuit, which means we need flip-flops. So usually in each CLB, in each configurable logic function, logic block, there are flip-flops there. There are flip-flops, optional flip-flops. So we include the flip-flop in each CLB, but you can bypass this flip-flop using a multiplexer. So this is a multiplexer, 2-to-1 multiplexer. It's controlled by this select signal. So if the select signal is high, you say you select one of them, or you select. So is that say if select signal is high, you select the flip-flop output. If not, you select this output, the combination output. You bypass the flip-flop. The general idea is to include flip-flop in the fabric. I would call it fabric of FPGA, like a woven away of fabric in the fabric to control programmable components. So the flip-flop is also programmable in the sense that it can be used or can be bypassed. And to program whether or not to include the flip-flop, well, we need another register or flip-flop here to control the multiplexer. And this register or flip-flop can also be programmed so that to use or skip the flip-flop inside the. This is a flip-flop used in digital circuits, and this flip-flop is to store data. It's a memory cell in order to control some multiplexers in the logic block. Okay, we talk about the use of multiplexer to select to select paths, and the multiplexer in actual hardware can be like this. Let's take a 3-input lookup table. This symbol is called transmission gate. You know what the transmission gate is, right? It is NMOS. So this is NMOS in parallel with a PMOS and PMOS in the bottom. So this is a control signal, and we have an inverted control signal to the gate of PMOS. So if the control signal is high, then this path turns on. If the control signal is low, the path turns off. We need a PMOS in order to have rear-to-rear signal swing, the wide swing of the signal. If you use NMOS only, when the transistor turns on, the signal at the source cannot be greater than the VDD minus threshold voltage. That's some circuit issue. But anyway, so here is just a transmission gate. This is another transmission gate. With a bubble here, meaning that the control signal is inverted. So here, this signal A enables one of the paths, one and only one of the paths. So we use this transmission gate, which contains transistors as multiplexer. This is one way to implement this multiplexer. So basically, this part This part is the address decoder. This ABC are the address inputs. That set of hardware is this transistor transmission gate address decoder, and we have 8 locations. And only one of this input, this memory is passed to the output for each input. So we store some values, 1 zeros, in these memory cells. It can be SRAM cells or register. You can treat it as SRAM. But for this particular circuit implementation, the advantage is that is simple and has reduced loading effect associated with this memory cell. So this memory cell is some kind of transistor circuit. If the low capacitance, say if here we have a wire here like this transistor drain and source, those drain and source and wire, they all present capacitance to this node. They present a capacitance to this node. And if that capacitance is large, then the reading speed, the reading speed will be slower. So with this transmission gate implementation, the advantage is the low capacitance is small. Okay, I think time's up. We'll stop here. So today we introduce this simple but very fundamental, important concept in the FPGA implementation. It's lookup table. We store some data in a small block of memories in each cell, and we can program. We can write those right into those memory locations. Okay. So that's all. Thank you for coming. I'll see you tomorrow.